Are we going? Hello. Thanks for putting away all your electronic devices. Really quick, I want to remind you of some things. Early out on Friday. How many of us are pulling for early out on Thursday? Me too. I'm super excited. What, Asa? An extra early out. That's right, an extra early out. Today, your capture question says list the 3 different types of boundaries and the movements of the plates at those locations. I think this is going to be an easy thing. There are 3 different types of boundaries that we looked at yesterday on the maps. So if you could get that out, that would be great. And then just draw some arrows as far as like the movements, and we'll go over that. We're going to do our capture question. Then we're going to do a little review of the modern theory of plate tectonics, and then we're going to look at some seafloor spreading, reading, and some questions. To remind you, I'm going to hand back essays, and if anybody in here still has not taken that quiz from last Friday, I've now got your name up on the board, and so I've got some people that need to go ahead and get that quiz done, and the essays. So I've got your essay, your names up there. If you have an essay to turn in right now, I would love to be able to have that essay from you in my hand. Do I see it printed out? All right, so please make sure that you get your essay done. I want this turned in by Friday, please, so that I can go away for break and everything is in the grade book. I was talking to some of the other teachers in science, and they're like, yep, if they don't get it turned in by Friday, everything's a 0. And I was like, wow, that's really harsh. But if we can get that taken care of, I would really appreciate it. So thank you very much to Kayla for turning yours in, and then anybody else get that done. Okay, what are we doing today? Students, you're going to learn the features of the seafloor that provide evidence for seafloor spreading and the plate tectonics, and plate tectonics, and we're going to talk about how those features are formed. Our language objectives, meaning how are we going to do that? Students will practice reasoning through evidence to draw conclusions by reading and writing down notes on seafloor spreading. So let's go ahead and get started by writing down our daily capture question. I'm going to put 1 minute on the clock starting now so that I can go ahead and take attendance and you can quietly do your reflection. My thing I'm wondering about, I know I said I was going to be quiet, is why don't they just call school now if we know that this big blizzard is coming our way? So that people that are traveling can really jump on the travel. What? But I don't get paid to make those decisions. All right, my dears, I'm going to go ahead and use this side of the board because that side of the board is filled. Can someone tell me what's one of the boundaries, one of the plate boundaries that you learned about yesterday? Let's get someone who's not really getting involved. Plate boundaries, there's 3 of them. Give me one, give me one. One, can I have one. Asa.
Convergent.
Let's go ahead and talk about that one. That's a good one to start with. Convergent boundary. Somebody other than Asa, can you tell me what are the movement of the plates at a convergent boundary? Will?
They are moving towards each other.
Moving towards each other, or I'm going to say coming together. And the reason I'm going to use the word coming is because it begins with C and so does convergent. And so for my arrows, I'm going to do this. This is what happens. Now, depending on the density of these 2 different plates, you can have different things happening, and we're going to go ahead and talk about that in a couple of days. It's all about the density, baby. Give me another one! Yeah. Braden, give me one.
Divergent.
Divergent, that's another good one. Divergent boundary. Now, somebody other than Asa and Braden and Will, tell me, At a divergent plate boundary, what are the plates doing? Ethan?
They're moving away.
Yeah, they're moving away or dividing away. So they're dividing away from each other. D for dividing, D for divergent. And so they would look something like this. This would be your situation at like the Nazca plate and the Pacific plate. That's what's happening there. This would be your situation between the Nazca plate and the South American plate, and that makes the Andes Mountains on the edge of the continent of South America. Last one was the very last one. Nope, you already participated. And I appreciate you, but you've already participated. So what's the last boundary that for sure is going to be on the quiz, absolutely, definitely going to be on the exam? It's the last boundary. Not coming towards each other, not moving away from each other. What's that last one? Rebecca? Yes, ma'am. Transform boundary. Awesome. That's the most difficult one to remember. Transform boundary. Here they slide past each other. You could have something like this, where one's going in one direction, one's going the other direction. This is what's happening to the island of Haiti. The whole island is literally kind of like sliding past each other. Terrible earthquakes in that area. You can also have something like we have with North American plate, where the North American plate is going in this direction and the Pacific plate is going up in this direction. They're still sliding past each other. Either one of those, if I show you an example on a quiz or an exam, would constitute a transform boundary. How's that feel? Pretty gosh darn good. Did anybody notice I've got my twinkle lights up finally? Thanks, Asa. It's that time. I remembered everything, like my lights today, my sugar cookies for my advisory class, like all of these things, and then I forgot my lunch. My light. Eat the cookies? No, the cookies are so my advisory class can like decorate cookies and then bring them around to their favorite teachers. I know, right? That's gonna be nice. All right, so that's that. Let's go ahead and hand back your essays. For those of you that got your essays done, thank you so very much. I'm gonna put those back in your hands. Nice job, nice job, nice job. For those of you that have not given me your essays yet, please get those taken care of and turned in. Could you give that to William right behind you? I'd appreciate that. Could you please hand that down to Kylie? I know you want to go somewhere right now, but you can't go. You can't go right now. Why do you have to go like right now during class when you should do it on your own time? This is your only time is when I'm doing other things. Go quick. Go quick. Maya. Oops, sorry. That was awful. Go. Wait, why aren't you going? You said you needed to go somewhere. Go. Could you give that to Braden behind you, please, behind you and over, and then give that to Cooper right behind you. Thank you very much. Could you hand that all the way back to William and then Peyton? Could you hand that back to Billy? And then could you hand that back and then over to Rebecca? And then here is yours. You're welcome. Your last paragraph was lacking. All right. We are going to go ahead and take some notes, and the notes we're going to take are called Modern Theory of Plate Tectonics. This is on the back side of your continental drift notes. So I'm going to show you in your table of contents where that might be so that you can see it. In our TOC, oh, it looks like my notes were not working very well. Hi, darling. Just put it down there, sweetie. All right, so I need some help getting caught up. I believe on 12:15, we had two things that I handed out, yes? Or one thing that I handed out was this notes on continental drift. And then on the back of this piece of paper are going to be, or is going to be, our modern theory of plate tectonics. And then, did I hand something out on the 16th, or was the next thing the 19th?
It's charting the ocean floor
The 19th?
on the 16th.
On the 16th? Thanks, darling. And then on the 19th,
Party with the plates.
what?
Party with plates.
Party with the plates. That was what we did yesterday with the map. And I believe that was on page 19. And so that was 1920, this is gonna be page, nope, yeah, page 21. Let's go ahead and write page 21, because today we picked up seafloor spreading. This was is going to be a reading that we are going to do. I think this was page 15. What was modern theory? Was that page 14? Was it? Whatever. Thanks, man. I appreciate you. Thanks for putting your name on it. I will take you off of the board. And you too, Kayla. Amazing. All right, so there's our table of contents. Let's go ahead now and go to the backside of continental drift notes and look at the modern theory of plate tectonics. I will show you what it looks like so that you can find it in your... Where is it? Where is it? Where is it? Where is it? Here. This is what you're looking for. You gotta open up your notebook. I gave it out a while ago. It's on the back of continental drift notes. Yep, it's that one. So this is on the back of your continental drift. We handed this out a while ago, so if you don't need to get another one, don't get another one. It's on the back of continental drift. So it's on the back. You already have this, y'all. It is on the back of these notes right here. So we took notes on continental drift, and it's on the back side of that. I know you have these notes. But you just don't want to look for them. Oh, what is up with you? Box it up.
I don't have it.
All right. So this is what we're looking for. Modern theory of plate tectonics. It's on the back of continental drift. It's on the back of continental drift, bud. There you go. It's on the back of that. All right. You're welcome. We good now? Has everybody got what they need? Good? Good? Asa? Good. You found it, man. I'm proud of you. All right. Modern theory of plate tectonics. Let's do it. Let's little review. So the modern theory of plate tectonics is built off of Alfred Wegener's theory of continental drift. William, I need you to be paying attention to what we're doing, bud. Okay, so that piece of paper that you have in front of you, what is it? 60 years is a long time, but 60 years is like not that long. Within the last 60 years, helped scientists develop this theory of modern day plate tectonics. So before that, we had no idea that there were convection currents in the mantle. So the first thing we're going to look at is your mid-ocean ridges. What is a mid-ocean ridge? It's a large mountain range at the bottom of the ocean. What? That's crazy. These mountain ranges rise up high above the deep sea floor. They don't poke their heads up through the sea floor though. They are at the bottom of the sea floor. Large mountain range made of volcanoes. As the earth is splitting open, magma rises up. Good? Mountain range. There's going to be a few slides now until we write something else down. So how do we know this? We know about the mid-ocean ridge because of Marie Tharp. Marie Tharp was what's called a cartographer. Has anybody ever heard of that word? She was a very famous map maker. At the time, she wasn't very famous, though, because it was the 1940s, 1950s, and she was a woman. And so, unfortunately, she had that going against her. But she was the first to detect the ridge in 1952. This is Marie Tharp, and these were the ridges that she had detected. So she was looking and making maps of the sea floor, just like you did. When we charted the ocean floor, she was also charting the ocean floor. Logan, get off your phone, man. She was also charting the sea floor and making the same kinds of maps that you made. Now, unfortunately, there was a man that dismissed all that she had done, but we'll get to him later. He was actually from Iowa. Jerk. All right, let's go ahead and see Marie's story.
1912, a German meteorologist named Alfred Wegener proposed a theory about how the Earth's landmasses formed. He suggested that the great continents of the Earth had once formed a single landmass called Pangaea, which had broken up and drifted apart over time. He called this process continental drift, and it went against all conventional thinking of the time, making him very unpopular amongst his peers. It's a shame because he was absolutely right. But it would take the work of a young cartographer called Marie Tharp to help turn the tide of opposition, leading to one of the greatest paradigm shifts in the earth sciences, and it all began at the bottom of the ocean. Marie's father worked for the Department of Agriculture, and from a young age she'd join him on his work trips as he travelled around the country collecting samples for soil survey maps. These early experiences were formative in developing Marie's interest in geology, and after gaining a master's degree in the subject, she landed a position at Columbia University in 1947. Here she worked as an assistant to Bruce Heason, a geology graduate who's collecting thousands of depth measurements across the Atlantic Ocean. During expeditions, Heason and his team used echo sounding to collect depth data, which involved sending out high-frequency sounds or pings and recording the time delay of the returning echo. The data could then be plotted to build a profile of the terrain below. Unfortunately for Tharp, women were prohibited from joining these early expeditions because of a fear that they'd bring bad luck at sea. Instead, she remained behind at the university to process the data, converting endless rows of depth measurements into detailed profiles of the ocean floor.
Just like you guys did.
Conventional thinking had once believed that the ocean floors were flat, featureless plains, but Tharp's maps were beginning to tell an entirely different story. Her profiles revealed the existence of a complex geography of crevices and valleys, but perhaps most startling was the emergence of a long V-shaped cleft that ran through each of her profiles. These so-called rift valleys offered support for Wegener's continental drift theory. If two landmasses were moving apart, they'd split the ocean floor in two, tearing a scar in the landscape and forming a valley below. Was this evidence for the controversial theory? Tharp believed so, but Heason was sceptical, dismissing many of her suggestions as girl talk. Nevertheless, Tharp was convinced by her findings and later produced a more detailed physiographic map to further support her case. At the same time, another graduate student, Howard Foster, was plotting the epicenters of earthquakes in the same region of the Atlantic. Tharp noticed that they occurred at the same location as her proposed valley, and as they expanded to other areas, they found something interesting. Where there were mid-ocean ridges, there were also earthquakes. so it seemed as though these two were related. At this point, even the sceptical heathen could no longer deny what they were looking at. A pattern of scars that spanned the Earth's oceans, permanent wounds torn into existence through the process of continental drift. The findings were finally reported in 1957, but opposition from the scientific community was still fierce. Renowned explorer Jacques Cousteau was so sure they were wrong, he chartered an expedition to film the ocean's floor to settle the score once and for all. But the footage he brought back did the opposite. It showed the deep valley, it showed how it split the mid-Atlantic ridge in half, and it showed that Tharp's maps were right all along. It was exactly where she plotted it. As the evidence mounted, a paradigm shift in the earth sciences was inevitable. Tharp's steadfast determination had paved the way for Wengener's continental drift theory to gain traction, and as the tide of opposition waned, it gave birth to our modern understanding of plate tectonics, and secured Tharp's position as one of the most outstanding cartographers of the 20th century.
So that's Marie Tharp.
1912, a German.
All right, so here's the next thing you're going to write down. Notice it's underlined. Sonar imaging was the technology used to discover the mid-Atlantic ridge. And this is what the mid-Atlantic ridge looks like through sonar. You can kind of see this scar shape that's happening. And so it is this mountain ridge at the bottom. And in the middle, you can see that valley that Marie Tharp had talked about. It's kind of like that cleft or that V in there that just keeps splitting open and more magma oozes out as the ocean is spreading. All right, so don't write anything down now for a little bit. Mid-Atlantic Ridge. This is Iceland. Iceland sits on the Mid-Atlantic Ridge. The magma from the ridge combined with a hot spot that is underneath Iceland. Hot spot is a huge upwelling of magma from the mantle. Is pushing the land above the ocean surface. And so this is just a big island that has been created because it's on a hot spot and it's also at a divergent plate boundary, with North America moving in one direction, Eurasia moving in the other. This is the only place that there is a ridge that you can actually see from the land and you can walk up to, but you can also swim in and between those ridges at that point. Has anybody ever been to Iceland? Nope. I had a couple of my students in last class do that. You can go there, and it's weird that they call it Iceland because it's just so many volcanoes in this area. But yeah, you can go there and swim in the Rift Valley if you'd like. Or not Rift Valley, in the ridge. Okay, Mid-Atlantic Ridge. Describe the movement of the magma underneath a mid-ocean ridge. So what's happening here and here? Think about them as gears in order to make this mid-ocean ridge. Please turn with your pair share partners and talk that out. Ready, set, go. 5, 4, 3, 2, 1. Well, that was totally lame. So what's going on with the direction of the convection currents in that area? What do we think? Asa? Yeah, they're spinning opposite and away from each other. So one's going like this and one is going like this. Big gears that are kind of like pushing away. We've got ridge push right here. They're pushing the ridge away from itself. All right, good job. Oops. All right, so what we're going to do on this big block that you have in front of you is we're going to go ahead and draw a picture. Start with drawing some mountains at the top, and then I want you to draw this. Does everybody see that big box in front of you? Don't worry about drawing the complete convection currents, because we're going to do a little bit more drawing in here. But just go ahead and put those mountains, and then we've got an upwelling, and they're moving apart like this. That's what we need you to do. When you've done that, we're just going to go ahead and label the mantle as the mantle, and we're going to go ahead and label the mid-ocean ridge where the mid-ocean ridge is. Keep it simple. Draw me a picture. All right. The second piece of evidence is ocean trenches. Wherever land splits, it's got to come together someplace else. So ocean trenches, this is the location where the Earth's crust is pulled back into the mantle. This is what's called slab pull. And this is called subduction. This is a zone or an area of subduction. This is very important that you understand what subduction is. Thinking about it like it's ducking underneath this, this extra plate over here. So the continental plate in this case is very much thicker, but it's less dense. And so continental plate less dense, it's got those rocks like granite, if you remember from our density of Earth's materials. Oceanic crust is much more dense. It's got materials like basalt. It's what's called mafic. So it's got a lot of iron and magnesium in it. It's much more dense. This will then sink underneath the continental crust, which is less dense. As it sinks underneath, it's going to get closer to the core, the hot area of the magma. It melts, and that melting magma is less dense, rising up through the cracks of the continental crust. Man, just like, put it away. And then it's going to create mountains on the edge of that. And so we've got that kind of thing going on over there. And this is an area where we've got like the Nazca plate coming together with the South American plate, making the Andes Mountains on the side of South America. All right, so here's an example of the Caribbean plate and the North American plate. North American plate is being pulled under the Caribbean plate. Here's Cuba, Puerto Rico. So all of this is going on underneath the water. Lots of earthquakes in those areas. I want to show you James Cameron. Has anybody heard of James Cameron? He's a director, movies. He went down to the Marianas Trench. Has anybody ever heard of the Marianas Trench? What do you know about it, Will?
It has the deepest point on it.
Deepest point on our planet.
Welcome to our show, and thank you so much for being here. You and your team have made history. You've done something historic. And what a
So
great...
it appears, like doing 100 shows.
Hey, thank you.
Congratulations.
Thank you very much. I appreciate it.
May you do 10,000 more.
Thank you so much. But this thing, when you watch this, I was just mesmerized. What a great group of people you have working on this too. Just you made your own submarine. You made your own. Because you want to go to the deepest part of the ocean.
Everybody acts like that's strange, but you know when you...
Yeah, no one makes their own submarine.
I never get this from kids, because kids say, well, why wouldn't you make your own submarine and go to the bottom of the ocean? You know,
I guess so,
they
yeah.
get it.
Is the Mariana Trench?
Yeah.
That is the deepest, because that's where the deepest part of the ocean is.
Yeah, Mariana Trench is long. It's about 1,500 miles long. There's a part of it called the Challenger Deep that's the deepest place on our planet.
And how deep is 35?
35,800 feet, something like that.
35,000
About 7 miles.
feet.
You were there.
Yeah, I checked it out.
And he got to the bottom of it.
I get to do that too, right? I'm here. I'm on the Tonight Show.
But I mean, you did the Abyss. I mean, you've done so many fun, kind of
Has everybody watched the movie The Abyss?
movies, but they're fictional.
Yeah, but this is sci-fi for real.
I mean, it freaked me out when I was watching.
Yeah.
It's you're in like kind of like the fetal position, you're like a little ball.
Sometimes I was, if things weren't going well.
But I mean, they had to make a sphere, so what? It just wouldn't, because I would be afraid it would explode.
Yeah, the sphere is really tiny. It's about 43 inches. It's like this big. You know what I mean? So you spend, you're kind of like...
You're shoved in there with like a remote control thing with cameras.
Yeah.
But you're smart. Well, actually, we have a model of the thing. So I really geeked out with this
check
movie.
this out.
Yeah, I made this the other
You made
day.
this?
I was goofing around with some paint and
Yeah, that was the prop
So
department.
this is it. So why vertical? Why not a sideways submarine like normal submarine, like the Beatles?
Yeah, most subs kind of go like...
Yeah.
And why not yellow?
And why not yellow?
Why
Yeah.
not yellow, right.
It looks beautiful though, lit up in the water.
Yeah.
Yeah.
Kawasaki Racing Green.
Kawasaki Racing Green.
That was the concept, right?
Good. Yeah. So you went up and
So
down.
vertical to go fast, you're going down 7 miles. So I wanted to have time to explore when I got down there, because I didn't want to spend any more time cramped up in that sphere than I had.
Yeah. So like a submarine, you'd be like this.
Yeah.
But your guy goes Like that.
Yeah. How about that fast?
How
too, yeah.
long does it take to get to the bottom?
It was about 2.5 hours to get down, about 3 hours on the bottom.
James. What part did you freak out and go, that's it, my life's over, and I can't communicate with the outside world, and I'm down here with aliens, and we're looking at each other, and that's how perfect ending to my life?
Yeah, exactly. It all made sense at the time.
I mean, when did you freak out? Could you talk to your, because I know you say goodbye to your wife.
But
You kissed her.
Susie was with me on the ship,
Yeah.
on the expedition,
Oh, yeah.
and she kissed me goodbye when I got inside the sub, and then she like grabbed the mic and called me when I was 7 miles down to give me a greeting,
Which is,
it was so cool. You know, I mean, just to hear her voice, because I'd heard like the comms guy, who's like was this ex-Navy guy, so I was like, yeah, Roger that. Said, I'm on the bottom.
Yeah.
The depth is 35,000, whatever, however many
Well,
feet.
that was the thing I thought
And
when
he's
you-
like, yep, Roger that. And then
You're
I
all
hear,
a little emotion.
yeah, Roger that, check.
Yeah, no. You want something to say, I can't believe it, oh my God.
Right.
That's, you gotta get me,
Yeah,
right?
right.
That's what I'm good at.
So
Yeah, you gotta call me
you
next
call
time.
next time.
I was screaming to that thing, like,
We'll
oh
put-
my God, good buddy, you did it.
We'll put you in the sub if you want to hear some screaming.
No, I mean, please, I will scream. But, I was shocked. You got to the bottom. They tried this to go to really deep. How far did they go? 1960 was the last time.
1960, they went to exactly the same depth in a different place about 30 miles away. And we thought it was going to be a little bit deeper where I dove, but it turned out to be exactly the same.
Exactly the same. But as soon as they landed, there was so much sediment around them.
They couldn't see
You
it.
couldn't see this up clouds out the window, and they had to go right back up.
I figured if I'm going down there as a filmmaker, I got a rep. I'd better come back with some pictures. I can't land in a big cloud and come back with nothing.
But you also took soil samples or whatever it was down there, sediment or whatever.
Yeah.
You had this trap with a chicken in it. I'm not making this up, right?
Yep.
And what attacked it? It was like shrimp type
Well,
of things?
it was in an earlier dive at 5 miles depth.
Yeah.
That these big amphipods, this big, came in and just stripped that chicken like piranha. Just like,
No, when you see this thing, there's just a carcass left.
Yeah.
Perfect bone with nothing, no fat, anything.
Crazy,
What
nothing.
are those amphipods?
amphipods. Yeah.
Amphipods.
So the whole
Gosh.
burial at sea thing, you
They look
might
like
want
sea monkeys. They
Yeah.
look like giant sea monkeys.
Giant sea monkeys.
Yeah,
That's
just
what they
big.
are.
So he went down to the very deepest part of the ocean. Let's go ahead and see some pictures. So this was the sub, and there was the little area that he was in down here, and so that was what he was doing. He was looking at the very bottom of the ocean and collecting samples, and I mean that's the coolest thing ever. All right, so what we're going to do is we're going to draw that. Notice that now what we've got is we've got some trenches that are happening. So, whoops, I forgot my last little bit. We're going to add this, and so you've got like this right here is another plate, and so this would be the trench. As this thing is being pulled, this is slab pull under, and this is slab pull under, and it's being pulled under this overriding plate. And those are the trenches, represented by these little lines. And if you ever watch The Abyss, it's super scary. It's like back in the 80s or something, but it's about this like aliens that live in the trenches. Yes? But James Cameron is the one that directed it. Good? So this is why the earth doesn't keep getting bigger and bigger and bigger. If more, land is expanding out, right, the planet would just grow. But where new land or new crust rather is being created, old crust is being recycled. So the ocean floor is going to be some of the youngest rocks on the planet because they're constantly being created and then destroyed. Right, so if we want to find old rocks, we got to go ahead and look at the continents, the land, dry land portion of it. All right, so then stop and check. Where in this picture is the mid-ocean ridge? In the middle, that's right. This is the mid-ocean ridge right here, where we've got some upwelling. We've got that ridge being pushed apart. All right, where are the ocean trenches? On the edges, yeah, you can see that this slab is being pulled under in this little V shape right here. This is a trench, and this is a trench, which looks like nothing, right? But imagine like 35,000, feet into the crust. Okay, at which point is the crust most thick? A, B, or C? It's actually A. Everybody say A? Yeah, it's A. At which location is the temperature the highest temperature? C, that's right. It's being created right here. Fresh, hot crust. All right, let's do a check. You got a matching section down there for ridge or trench. Where's the youngest crust? At the ridge or at the trench? The ridge is the youngest crust. So please write the word ridge or R. Well, you're with me? We're at the bottom. Matching. Oldest crust, ridge or trench? Trench. T or trench. That's where the oldest crust is. It's been traveling along the bottom of the ocean for a long time. Nice, cool, dense ocean crust. The coldest? Trench. Just kind of gave that away. It's been around for a long, long time. So if you have two ocean crusts coming at each other, the most dense one, which is going to be the older or colder one, is going to go below the younger one. The warmest is going to be what? Ridge or trench? Ridge, that's right. And then the thinnest? Ridge again is going to be the thinnest crust. And that's it. Oh, I'm sorry, the thickest is at the trench. And then what we're going to do is get out that seafloor spreading reading that we picked up on the way in. Which is this, my darlings. Get this out. All right, I'm going to go ahead and read this for us. And then you've got some questions on the back to answer. So, the longest chain of mountains in the world is the system of mid-ocean ridges. In the mid-1900s, scientists mapped the mid-ocean ridges using sonar. Sonar is a device that bounces sound waves off underwater objects, then records the echoes of these sound waves. You use that data to chart the ocean floor when you made your own chart of the bottom of the mid-ocean ridge. The mid-ocean ridges curve along the ocean floor, extending into all of Earth's oceans. Most of the mountains in the mid-ocean ridges lie hidden under hundreds of meters of water. A steep-sided valley splits the top of some mid-ocean ridges. This is what Marie Tharp found. The Earth's ocean floors move like conveyor belts. Does anybody know what a conveyor belt is? Yeah, it's like when you put your groceries in the grocery store and it moves your groceries down. That's a conveyor belt. So the Earth's ocean floors move like conveyor belts, carrying the continents along with them as they move. This movement begins at a mid-ocean ridge. A ridge forms along a crack in the ocean's crust, just kind of like how your skin cracks. At mid-ocean ridge, molten material rises from the mantle and erupts. The molten material then spreads out, pushing older rock to both sides of the ridge. As the molten material cools, it forms a strip of solid rock in the center of the ridge, kind of like if you have a scab that has scabbed over on your cut. Then more molten material can split apart that strip of solid rock that formed before, pushing it aside, kind of like if you split your scab and more blood comes up. This process, called seafloor spreading, continually adds new material to the ocean floor. Scientists have found strange rocks shaped like pillows, it's actually called pillow lava, in the central valley of mid-ocean ridges. Such rocks can only form if molten material hardens very quickly after erupting underwater. The presence of these rocks supports the theory of seafloor spreading. More support came when scientists discovered that the rock that makes up the ocean floor lies in patterns of magnetized stripes. What? Magnets on the bottom of the ocean floor? Let me explain what they're talking about. When magma when rock melts, there's iron in it. And as it cools, the magma, or the iron in the magma, rotates itself so that it points north and south. And so that's what they're talking about. It's magnetized. It's got like a north end and a south end like a magnet. The pattern is the same on both sides of the ridge. These stripes hold a record of reversals in Earth's magnetic field. The final proof of seafloor spreading came from rock samples obtained by drilling into the ocean floor. Scientists found that the farther from a ridge the rocks were taken, the older those rocks were. Let's go ahead and move down a bit. Oh, too far, missing brain. The ocean floor does not just keep spreading. Instead, it sinks beneath deep underwater canyons called deep ocean trenches. Where there are trenches, subduction takes place. Subduction is the process by which the ocean floor sinks beneath a deep ocean trench and back into the mantle. At deep ocean trenches, subduction allows part of the ocean floor to sink back into the mantle over tens of millions of years. The process of subduction and seafloor spreading can change the size and the shape of the oceans. Because of these processes, the ocean floor is renewed, meaning redone over again about every 200 million years. The Pacific Ocean is shrinking. Its many trenches are swallowing more ocean crust than the mid-ocean ridge is producing. The Atlantic Ocean is expanding. In most places, the oceanic crust of the Atlantic Ocean is attached to continental crust. As the Atlantic floor spreads, the continents along its edge also move. So flip over that paper, please. You have got a picture on the front side, or excuse me, the back side, and it's got some letters on it. So you are going to go ahead and look at that with the notes that we took, with the information that you have, with the reading that we had on the front side. You are going to work through and answer these questions. On your marks, get set, go. You can work with your partner, or you can work individually alone if you want. If you don't finish in class, that's your homework for tonight. This is homework for tonight, if you don't finish it in class. Oh, please tell me I didn't break it.
Okay.
There we go.
A is mid-ocean ridge, like the